Hey, good morning. Or no, geez, it's afternoon. Good afternoon. Hopefully your day is going well. Just doing that. You can hear me okay?
Yes, I can. Thank you.
Yeah. Okay, so what I'd love to do is to just start with the normal thing where I'll share a screen and go through a couple administrative sort of announcement-y type things, and then dive into newish material if that's what you'd like.
Perfect.
Darling,
Thank you.
I I probably should do the share screen thing. Mhm. So that should be showing you, well, what I'm seeing. Haha. And I should have updated this one thing about office hours last week because office hours this week are not intending to adjust those at all. But you know what? I didn't do that. Week five. Geez, it's week five already, which means we've got just a couple days before our final exam. This week, new material, the last chapter in our textbook that we're going to focus on. And because students in past terms uniformly tell me they prefer logistic regression as a last topic to chapter 12 in our textbook, we're doing logistic regression, and it makes sense. It's basically we've built all this machinery where with the general linear model we could talk about predicting a y or estimating the relationship between x and y. Logistic regression basically is the same deal, except for what if your y variable, your response variable, is categorical, like a success or failure, living or dead, group A or group B. We can sort of assess relationships there in those contexts as well. But getting out of the specifics about this week, the first part of the week, just want to note this exam is coming up. Want to sort of make sure that we're all on the same page. Today, indeed, it's choosing variables and then working towards building a model. Then next time is, well, what if your response variable is categorical? Wednesday, it's entirely questions by way of review material, things that you would like to know about as a way of getting ready for the final exam. Because Thursday, there's this in-person final exam. I should really find out what the building is. I'm pretty sure it's the science Baker Science Building, and which room. I think it's on the ground floor, but I will get you all that information. Oh, it might even be in here. It doesn't say. Oh, it does say Building 180 at Baker and then room 113 on the ground floor. There will be office hours next week on this week, geez, on Thursday before our exam. So at least an hour before our exam, there will be some office hour opportunity. And then after our exam is over, if that's your preference, there will be an additional time to sort of chat with me later. I expect that that's not going to be urgent, but any things could be resolved via email. Okay, with all that in mind, you may have one more thing, and that is our exam two answers are here. If it said it's auto graded, sort of what the answer is, but those answers where you were to fill in or write something, a short answer, I wrote out, oh yeah, here is the thought process. Okay. And so I'm absolutely happy to tackle any questions you might have on the exams, especially in office hours. Today, Tuesday, Wednesday, or Thursday before the exam, or Wednesday during the review portion. Going over those exam one and two fill in answers would be good in addition to the final exam. So you can click your way into that. And I don't the sample final exam. Here are those questions. Look them over. We'll talk about that on Wednesday. Okay. So, any administrative questions before we sort of talk about other sorts of questions, subject matter questions? Okay. Are there any subject matter questions related to content from the recent past? like last Wednesday, Thursday class, because y'all have homework due tonight by midnight on those last two topics. Or I guess the last topic, chapter 10 content. Okay, so let's get into current content. And again, in the context of what's going on, the notes here should be right available, and you could take notes on those notes if you like. And then soon a video of today will appear, but also you can watch content from a couple years ago, or actually 3 years ago or 2 years ago if you'd like to, and it's largely comparable. Okay. In chapter 10 and 11, we're doing a couple things to sort of like put it all together. In chapter 10 last time, I call it design of experiments advanced, part two. And we're dealing with what if your explanatory factors are quantitative and you pick different levels. And we saw that, oh, yeah, we can do fancy polynomial things and there's benefits of doing that. There's other material that sort of is largely attached to fancy designing experiments, but that's covered in the design of experiments class, which now has a new number, but I think it's stat 3540. Okay, so that would be a class that you could take, but 3530 is regression, 3540 is design of experiments. Uh, Today, we're going to talk about, well, what if you don't have a design experiment, but we've got a lot of X's and you trying to figure out the nature of the best model out there. And there's only really two questions that I think are hanging out, hanging over our heads, if you will. And one of them is if you have many explanatory variables, which ones should you include in the model and which ones shouldn't you? And then how do you determine the nature of how the variables are included? Do you include them as quantitative factors? Do you add a quadratic? Do you need interactions? If it's categorical, do you need an interaction between the categorical factor and then this quantitative X? Uh, Building models is tough. Building models is tough. There are full-on terms of material. We're attempting to scratch the surface by way of introduction, so that way when you do go into your more later advanced classes, you can ask questions of your faculty members and say, well, when you developed that model, why didn't you include the interaction? Or perhaps were the researchers who were doing this, were they aware of the fact that they tested many separate hypotheses, and so maybe they should have adjusted their p-values? We're sort of trying to get you ready for the questions that an actual researcher would be wanting to ask of their data, or a researcher would want to be asking of the person who did the study. Okay, so we're assuming that you have the following concepts and some understanding of them. Um, is it quantitative or is it categorical? Yay. Linear. Oh, what about quadratics or higher order terms? Interactions in general. Model hierarchy, where we sort of we touched on that one lightly this term because it's summer. Model hierarchy basically means simpler terms first. Quadratics and cubics or interactions follow the simpler terms. So if you have the interaction between x1 and x2, x1 and x2 should precede the interaction, because then you're dealing with model hierarchy appropriately, and sequential sums of squares will be entirely appropriate. Sometimes sequential sums of squares is indeed the way we need to proceed, because you want to control for some, but not all of the other x's. Put the simpler ones that you want to control for preceding the one you want to test for. And there may be a need with sequential sums of squares to run several analyses based on the exact other x variables you want to control for. Okay. Also be aware of correlated x's. Okay. What else? We're pretty comfortable with residual analysis. We've looked at those back into week one this term. But yeah, in chapters 8 and 9, here's how we can actually use residuals to identify that we need maybe a quadratic term. Here's how we can identify perhaps that a transformation might be needed. We still have yet to tackle two questions today. Which x's should we start with? And how do you determine which is the best model if you are given a choice of two models? And what if they're not literal subsets of each other and you can't do a partial F test to compare the two? How do you determine which is the best model? What are some criteria you might want to consider? So let's get into that in a bit more depth. First off, I've overemphasized R squared this term. I constantly say, well, what's R squared? R squared is 83%. That's pretty good. I'm happy with that. If I said R squared is 12%, I would have been unhappy with that. I literally have seen real life data sets where the R squared was 0.99 and the researcher was unhappy because it was unable to explain 1% of the variability. And they believe they should be able to explain a greater fraction because it was nuclear physics and they want to be able to explain nearly 100%. They're not satisfied perhaps with less than 99.99% R squared. I've seen other situations where R squared was like 0.12 or 12%. And the fact that we could even explain 12% in the variability of some sociological variables was considered high or unusual. R squared is not a number that you could compare to other than maybe really comparable data sets in the same field. Don't compare R squareds across situations where you have very different models or very different data. One thing that we do know, though, is if we add an X variable into our analysis, R squared cannot go down. R squared will probably go up by adding an additional X variable. Literally, if you the only way to have R squared not increase is if the slope exactly of that new X variable is identically 0.00000, in which case I guess it's explaining nothing. Or if all of the effects for a categorical X are exactly 0.0000, then none of the groups are differing from each other at all, in which case we're not able to explain anything more with that new variable. So R squared always seems to go up, never goes down. But clearly, then, I guess if we tried to maximize R squared, we're going to toss every single X variable into the model. We're going to come up with a kitchen sink model. We're going to use every X in sight. And that's going to create too complex of a model. We'd like to believe in model parsimony, if you will, or keep it simple, stupid. The real issue is a model that has too many terms in it, is too complex, is maybe going to mislead because we're fitting randomness with a trend. If you choose to maximize R squared, you're going to keep putting in more and more and more terms, and you're going to add in a lot of insignificant X variables. And you're going to say, oh, yeah, the way that we would really predict the whether the stock market goes up next year or not is whether the AFC or the NFC wins the Super Bowl or in a given year. And that's actually true, that it is predictive across the last 35 years, you can follow that trend pretty well. The problem is, it's not really a real trend. Bad luck will cause you to sometimes overfit a model if you follow that bad luck. So let's not get misled by bad luck. We need an alternative set of criteria or one alternative criterion we could use. One of them is maybe the smallest mean square error. Literally, if we go with the smallest MSE, we're better. Another approach that's a little bit better than that is the highest adjusted R squared. What is an adjusted R squared? Well, it looks as though in our equation, R squared adjusted is 1 minus R squared times some ratio, okay? Total degrees of freedom divided by degrees of freedom for the residual. If your model has a large value for n, the total degrees of freedom is like n minus 1, okay? And the residual degrees of freedom would be n minus the number of variables in your model. So a large data set size with lots of observations, this ratio here is going to be quite close to 1, and r squared adjusted is pretty close to r squared. However, if the total degrees of freedom is, say, 20, because you got 21 data points, and if you only have 7 residual degrees of freedom, because you literally had 13 degrees of freedom in your model, your total degrees of freedom would be like 20 over 13. Okay, so I guess let's go with 20 over 15 because that's going to be easier to work with the math. That'd be like 1 1/3. So r squared adjusted, you could calculate that. Okay. R squared adjusted is sort of a hack of penalizing a model for excessive number of variables. Too many variables, r squared adjusted will be a lot adjusted lower than r squared itself. Okay. And so if you maximize r squared adjusted, uh, well, I guess if you have a new variable that you add in that increases the model complexity, it had better well gain you a lot in terms of how well you're able to explain the pattern in the Y's. And if you're not able to explain the pattern dramatically better, okay, r squared adjusted will actually go down. Adding a new variable will cause r squared adjusted to go down if it's not very helpful. So this is the first of the several methods we have for tackling model complexity. R squared adjusted is a bit of a hack. Okay. A slightly better approach to that is, I shouldn't say slightly, a much better approach to that is this thing called the Mallows CP. JMP will present that for you in something I'll show you today. The lowest value for Mallows CP is the best model according to that criterion. A fancier method for adjusting or selecting a model, I should say, is the lowest AIC value. AIC stands for Ake information criterion. BIC stands for Bayes information criterion. Sometimes it's called Schwartz-Bayes criterion. Press or complete cross-validation. Other methods out there. We're just saying choose the lowest. And in this class, I'm going to say AIC is what I would suggest. There are other contexts where choosing the lowest BIC would be more appropriate. And a whole new class might suggest cross-validation or press might be better. I'm just saying choose the lowest AIC model when in doubt. Last thing, I think another criterion would be, well, maybe we should only use models where all the X variables are significant or all the X variables are helping the X variables we care about be significant. So which X's should I actually choose? Well, shoot, if you want to test a hypothesis, okay, choose that X. If your hypothesis is about is this X related to Y, you have to have this X in the model to determine if it's related to your response. How about any theoretically necessary X variables? By theoretically necessary, we mean if there's someone in your discipline who says, oh, yeah, for sure, here's an X that does matter. The amount of moisture that you apply to the plants, the moisture in the soil, a tensiometer could be used to measure that. You might need to actually include that if your theory in your discipline, if the well-established understanding says here's something which you need, you got to have it in your analysis, or it will bias the XY relationships you want to assess. If there is an X which seems to be demonstratedly related to the Y, in other words, if there's an X that's statistically significant, yeah, keep it in your model. Unless an expert in your discipline says, no, you shouldn't. We say, as statisticians, if there's an X that you know is related to the response variable Y, keep it. And then lastly, I would say, if there's an X variable where by adding it into your model causes the p-value for the one variable you want to test. If that causes that p-value to be lower, it's clarifying the relationship. Controlling for this certain x allows us to spot this other one that we care about, whether it's actually related to the response variable y. What other x variables should we include? None. Well, that was easy. Okay. And we're not really considering even the question of interactions and transformations and polynomials and all that sort of stuff. We're just saying, should you include this term or not? If some of the terms are interactions or transformations or polynomials, it makes the model very complex. And I don't even want to go there, but we will bring it up in class in a little bit. So I like to sort of think about these algorithmic ways of choosing a collection of variables. It's sort of like Google Maps, or when we're driving along, we sort of like, well, we talk into the phone these days rather than punch numbers in. You tell the Siri your friend's address, and you say, "Okay, get me the route." And at first it says, okay, because I'm going to go with my friend Sean, who lives in Las Vegas. Never been to his house. It's actually in Henderson, but I think of it as Sean lives in Las Vegas. If I say, here's Sean's address, and I just talk at my phone and say, get me there, my phone's going to sort of zoom to the level where it says, okay, you sort of head basically east from California until you get into Las Vegas area or southern Nevada. Okay. But as we go, sometimes you could sort of zoom in on a portion of the journey. Like when I sort of zoom in initially, and this is the zoom in motion. Okay. When I zoom in initially, it says, okay, to get to my friend's house in Vegas, first take Highway 41 north from Morro Bay to 101 north to 46 east in Paso Robles, and then when we hit 5, take 5 southbound, and then get off on some road that's just north of Bakersfield and drive all the way down over to 99 southbound, and then we get on 58 east to Barstow, and then for Barstow we get on 50. So you get the idea. You know the basic route, which are the main highways to start with. Okay. That's sort of like the regional map. Hey, which X's to use? Which are the main highways I'm gonna sort of go on? And then when I get closer in towards Vegas, I'm gonna end up with it sort of zooms in for me because I always say please zoom in a little bit as we go, and it says okay, now you've entered the Vegas metro area. And you're near a Costco, and you just get off here, and there's a gas station, and the Raiders training facility, and a Costco, and you just keep heading east. Okay, I can handle that. I can say, okay, I get off here, I follow the instructions, and it gets me into eventually Henderson, where I'm sort of getting towards the town he lives in, and it says zooms in a little bit more, and it says, okay, here's a main three lane street that you go on. You go south by 2 miles, and then you sort of make an eastbound turn onto a 2 lane each direction street. Then eventually you make a left turn onto a 1 lane each direction street, and we go a quarter mile, and that's where he lives. Okay, so as we go and go and go, we're sort of picking which X's to use at the first level. Second level is, okay, do we literally need another X? Is there one that we forgot? Maybe we need to do some hypothesis checking, okay, hypothesis testing by way of say, do we need a quadratic term? Or do we need an interaction? Once we feel pretty good about the model overall, then we're at that local view and we can test the hypotheses about the variables you have in the first place. So in class today, we're going to talk about forward selection, backwards elimination, stepwise regression, and then best subsets. These are ways of choosing which X's. Which X's do we want to use? Forward selection, it's sort of like this. Each individual variable, we could say, do we want to include it or not? Okay. And the question is, when we're moving forwards from a model that's small, like no variables, into a larger model, a model with one variable, well, which is the best one to use? We'll just go with the one that's best. Okay. And once I have a model with one variable in it, how do I go to the best model with two variables? Well, I already have the one. Which of the remaining models do I want to include? Which of the remaining x's do I want to include as my next x? Okay, so let's maybe get into an example here and walk you through how you could use forward selection. These are data that we've looked at before in a couple contexts. Mortality, that's the response. That's mortality from lung-related disease deaths. Okay, so 790 is sort of on the low side, 890 is on the high side. Fort Worth has more deaths from these lung problems than does, oh shoot, Akron, Ohio, 920, even worse. So higher numbers, more death from these breathing related problems. And we really think the air pollutants might be related to mortality, but there are other things that cause some places to have higher levels of mortality than others. Maybe the people are older, you know? We found in earlier looks at the data that the log base 10 is probably the best way to measure these pollutant data from the point of view of their relationship with mortality. But there are all these other X variables that we looked at, like precipitation, humidity over 65. That's the rate of elderly. What percent of people are poor? Because I guess if there's people who are poor, the greater the rate of people being poor, the higher the rate of people who can't afford health care. And so you'd expect the death rate would be higher just because it's poor people. So there's a collection of different X's here, and I'm saying there's 15 of them. 15 separate X's. Which do I want to include? Uh, Forward selection basically says find the one X variable that does the best job. Add this in first. Then at the next step, choose the one X variable that's next to add in. Here's how I'm going to pull that off within inside GMP. I'm going to go with fit model. Like before, your fit model, okay, is basically just going to be you highlight the X's you want. You say drag them all over here into this set of model effects. And I'm not including any interactions or fancy things for now. We could do that later on, but it makes it harder for forward selection to do its job. The response mortality. At this stage here, I don't just go with click run. Under personality, I'm going to say, oh, no. Go with stepwise regression. All of the tools we're talking about today are under personality stepwise. I click run at this point in time. Run. And now what I see here is the setup for which variables I might want to include in my model. It's already done. It looks like an estimate of one sort or another. And that is, here's the average value of y, okay, under the condition of there are no x's involved in the model. And here's a collection of p-values of if this were the one single only x to be in the model, what would be its p-value? And I'm thinking choose the lowest p-value. The lowest p-value is the right way to go. So I'm going to go with p-value threshold, and I'm going to go with forward selection. I just click go. Boom. Sorry. I'm going to remove all. Boom. I'm going to click step, make one step. And because the p-value is tiny, for non-white percentage, okay, it's going to put non-white percentage in the model first. So non-white percentage is the first term in our model. And if we take another step, we're saying which of the remaining p-values. Now, these are all adjusted p-values controlling for non-white percentage already being in the model. Which one do I want to put in next? And my guess is house, because that seems to have the lowest p-value of all of these others. It's 4.86 times 10 to the negative 5. I take another step. Look at this. Not house. Education was the one that was put in next. And if I were to have a model with 1, 2 variables, what is the next one that I would put in? Well, 0.0083 does seem 0.0083 seems pretty low. Is there anything lower than 0.0083? Yeah, no, my guess is that's one, maybe the next log 2 SO2. Let's take a step. And indeed, log 2 SO2 is what was included next. So every time I take a step forward, okay, it's going to adjust all of these p-values, okay? And I'm going to say, well, I've already got 3 variables in the model. Which would be the next one to put in? Boom. So precipitation. I could step through the model, adding them as I go, yeah? And eventually, um, we're being told as we go, we entered non-white percentage first, then education, then log 10 SO2, then precipitation, then January temperature, log 10 nitrous oxide, etc. And we kept going, going, going. And luckily for us, we have this column called AIC. And we could go notice that as you add variables in, the AIC value drops. And 601.535 does seem to be where AIC is bottomed out. Maybe the best model is this one with the lowest AIC. We can select it and go back over here. And if you wanted, you could literally run that model and you get the lowest AIC model according to forward selection. Forward selection is computationally efficient because at the first round where we have 15 separate X variables, I'm going to do 15 regressions and I'll choose the one best of the 15. And then at the second stage, we've already added the one X variable and I've got 14 extra X's that I could try out. Yay, 14. 15 plus 14 plus then 13 and then 12 X. Every time we consider adding a variable, we try every single one of the remaining variables to see if things are better. How does all this contrast with backwards elimination? Backwards elimination is we're going to like put everything in the model. Let's literally put every X variable in the model that we have. And then we'll see which of you is worst. Well, you're worst. Get out of my model. You're not helping explain anything. Let's get rid of you. And you eliminate the worst variable. Then you eliminate the second worst variable, then the third worst variable. Backwards elimination is computationally more efficient because I guess I would want run one analysis with 15x variables. And one regression allows me to figure out which is the worst and get rid of it. Then the second worst and get rid of it. A second regression will be done. Every time we want to consider, do we want to remove an extra X variable? We just run one more multiple regression and we continue until we're happy or AIC is minimized or whatever that is. Let's try running this analysis with backwards elimination. Again, so under Analyze, Fit Model, I'm going to hit Recall. Boom. And that even puts me back in the stepwise world. Run that. And I'm going to say backwards elimination. Boom. And I want to start with all of the variables. So I'm going to put them all in there. And I'm going to sort of step by step remove the least helpful. And my guess is because I'm looking for high p-values, those are not helpful. White collar seems to have a high p-value. The first step, we remove the white collar variable. And then of the remaining p-values, humidity may be pretty high, 0.86. And then poverty or percent poor, 0.75. That seems like the highest of what's left. We remove the poor, and we could again step through the analysis, and we could keep going down until we have no variables left. And which variable do I want to use? Well, again, we're going to say using the AIC value that's minimized is the best choice. So AIC starts out 617 and then it gets lower and lower and lower down to 599.58 something and then 599.245. That would be the lowest AIC value. Boom. Let's go ahead and run that model. And interesting that our two models, one with forward selection and backwards elimination, it looks as though the best model, according to the AIC criterion, if we're using forward selection, has 1, 2, 3, 4, 5, 6, 7 variables. 1, 2, 3, 4, 5 variables for the best model with backwards elimination. It looks as though they're hitting different conclusions by telling us which are the best set of variables to start with, and that's frustrating. Let's look at a smaller analogy for a moment. What if I had exactly 3 X variables and 1 Y? The Y variable is, yeah, a person's salary. If I want to predict a person's salary and I'm using only their age, their years of work experience, yeah, and their education level. So three X's, age, work experience in years, and then education in years. Which X variables would be included? Forward selection would say, we put in age. We put in age first. And then you'd put in years work experience second, then education level third. Backwards elimination would remove age first. And at first you're thinking, well, why would that be? The reason is probably older people, yes, they do make more. On average, though, it's because either higher education levels or more years of work experience. Age is basically a proxy variable combining the two separate effects of education and years of work experience. The older a person is, the higher one of the other things will be. I mean, I could even predict a person's age pretty well. Their age is probably their years of education plus their years of work experience, plus five, the number of years they were when they entered school in the first place. So those three variables, age, first in with forward selection, also the first out with backwards elimination. And so it's a little frustrating here that the two methods produce different results. What about this stepwise procedure? It's formally a mixing of the two forward and backwards with stepwise regression. Basically, we're going to add an X variable. We're going to add a second X variable. And once we hit adding a third X variable, we say, hey, are any of the two X's that I already added, are they worth eliminating because of the combined impact of the other two earlier? Like poets and legs again, when you have multiple X's in your model, you might not need all of them. And one thing that you had earlier thought was important may no longer be seemingly important. So stepwise regression, basically it's forward selection, forward selection, forward selection. Do I need to eliminate? Forward selection, do I need to eliminate? And you repeat the process. You add something in and then check if it needs to be removed. So how would you try stepwise? Again, it's the same thing. So fit model. I'm going to hit recall. Boom. I've got myself set up. Mortality depends on my 15 friends over here. Stepwise, click run. And I'm spotting here, instead of forward selection, I could go with mixed. Okay, mixed. That's called stepwise regression, mixed. And I could go step by step by step. And let's just go ahead and try and see what happens. I'm sorry, you have to use, instead of minimum BIC, we have to use p-value threshold. So if there's a p-value that's below 0.25, you get in. But if it climbs above 0.25, we take you out. Okay. So we took a step, we put in non-white percentage, step. Notice it's entered, step. We're entering step, enter, step, enter, step, enter, step, enter. Maybe I'll make this bigger so we can maybe see if we remove someone. Step, enter, step, enter, step, enter, step, enter. Oh, we are not entering anyone anymore. And notice that we don't even get down to the 599 that we had seen earlier. Our stepwise procedure doesn't get us to where we were able to get with backwards elimination. So we've got these three flawed methods, 1, 2, 3 flawed methods. Why would you ever use the flawed methods? Well, because the next thing, which says best subsets, won't necessarily work in every case. Forward selection and backwards elimination are really always possible if you have a large number of explanatory variables and a very large data set size. It takes a while computationally, but it's a lot quicker than our next friend, best subsets. Best subsets is a real pain in the ass because literally, for each variable, you either include it, yes, or you don't include it, no. So each variable has two states. And if I have, like in this data set, 15 explanatory variables, there's 2 to the 15th power possible models. Well, minus 1, the model with nothing in it. So let's think that through. Remembering back to that game 1024 or 2048, one variable gets two possible, two variables gets four. Three variables gets 8, four variables 16, five variables 32, 64, 128, 256, 512, 10, 24, 20, 48, 40, 96. Oh, that's 81, 92, 16,000, like 32,000 models or something like that. Do you want to fit 32,000 regressions? Probably the answer is no. If you've got a computer and say to computer, run all possible regressions, it's going to say, I'll try. But if you have enough possible explanatory variables, remember we double the number of models we fit every time you add a new explanatory variable. All of a sudden, we're at 32, 64, 128, 256,000, 512,000, 1 million models. I don't want to have to fit a million models. For even 20 separate explanatory variables, you're going to be fitting on the order of a million models. You might not have the time for that. So best subsets only will work if you have a limited number of explanatory variables. Fortunately, 15, I think we can pull it off. Let's show you how to do it. Again, it's under our friend fit model. Again, you recall, which means you list off all your x's that you want to include or not include, your y's mortality. Instead of stepwise, well, yeah, we do a stepwise here. Stepwise, click run. But over here now, off to the very left, rather than forward or backwards, for whatever reason, they stuck it over here. Fit every possible model. Yeah, literally fit every possible model where each of these x's is included in a linear fashion or not. And so, how many number of variables am I willing to have in the model? Well, I'll go up to 15 because I got 15 x's. And how many variables do we want to see for each model size? Well, what if it's let's go with 2 for now. You could choose, up to 14 variables in your model and, best 3 if you want. I'm going to go with 15 and 2 because why not? And I click OK, and it seems like we alternate yellow and white, yellow and white, yellow and white. Yellow is the better of the two at that model size here. Non-white is the best one single variable. Okay, if you have to choose one explanatory variable, choose the non-white percentage. The AIC value is 639. If you couldn't choose non-white percentage, choose education as a variable. It will give you 653. Now, if we go to models with two variables, education and non-white, it seems like the best two individual variables, you add them together. In this case, we have an AIC of 624. But if I couldn't choose education and non-white percentage, log 10 SA2 and log 10 SO2 and non-white percentage does almost as well from the AIC point of view. So it's a matter of we choose the model that's best from whatever the criterion is. You might notice here, non-white percentage here, education there, non-white and education, log 10 SO2 precipitation and non-white percentage. We see that RMSE is dropping pretty quickly as we have more and more variables in the model. And eventually we get into this blurry zone where they're all about the same in terms of RMSE. If I was choosing for lowest AIC, I'm going to look in again for the 599. Do I beat 599.245? 599.245. I don't seem to be lower than 599.245. My according to best subsets model is this one here. Yeah, literally 1, 2, 3, 4, 5. These are the 5 explanatory variables we should use to start. Any questions about that so far? Okay, so we start with those. How many variables? 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5. We start with those 5 explanatory variables. It's like we're getting into Nevada out of California, but we need to try something. We need to check the residuals to see if our model really does make sense. Like the joke goes about the computer scientist, how do you capture one? You hand them a shampoo bottle, you put them in the shower, you say lather, rinse, repeat on the bottle. So they lather, rinse, and then they repeat the whole process, and then that includes repeat. Ultimately, what we have here is a situation where we have the opportunity to do this again and again and again. Use best subsets, get in the ballpark, pick some X variables, and then fit a model and look whether there are problems with our residuals. And if there are problems with the residuals, we might need to do a transformation of either X or of Y. We might need to fit a quadratic term. We might need an interaction. Or maybe there's a statistically significant variable that we had included. And then because of an earlier transformation and an interaction, all of a sudden this new X, which you hadn't earlier chosen, is important. So it does seem as though we like start with some X's, fit a model, look to see if there are problems, see if we can fix a problem. And if we can fix a problem, go back and say, now we are back at square one. And then we're going to check to see if there's any issues that we need to fix and circle around until we end up with something that's a relatively clean picture. I just want to note one last thing, and that is if our look for interactions or quadratics, yeah, cause us to effectively change our model, we might be able to use something like best subsets. Yeah, you literally could run best subsets with perhaps all of your possible interactions. That's a bit more algorithmic than I appreciate, but it is a way of moving forward. If you don't want to think through what your X variables are and what they really mean, and you're just interested in the lowest AIC value, yeah, we can probably use the algorithm of best subsets. Once you have chosen some X variables, try all the interactions. And then once you try the models, all the interaction models, try adding in some quadratics and go back and forth again until you end up with something that you're happy. I hope, however, on the lab, don't think I walked you through that. What I think I set you up for is one, the question is we want to know whether funding schools increases the quality of the schools. The way we're measuring that is on the lab, the SAT score that the state has as a whole, the average SAT score across the whole state. And that's sort of a bit of a bogus a response variable in one level because in some states, Iowa, students that want to go to the public universities in Iowa, they take the ACT, not the SAT. So the SAT scores in Iowa are pretty high because the only students who are taking the SAT are people who are intending to go out of state to college or to schools that are privates that don't have the ACT requirement. And so clearly we have to control for the percent of students that are taking the SAT when we're trying to assess whether the SAT is a function of expenditures. There are other X variables, of course, that are important in the lab, but the lab walks you through that. Okay. Um, Pausing for any subject matter questions, and then otherwise I got one question in the chat that I wanted to ask or answer before we leave. Okay, so for the exam on Thursday, literally it's going to be on paper, and on paper it's going to be like a short answer. Like you write an equation, you might have the partial F statistic and you plug in the numbers, you do calculations. It might be a short answer where you say, oh, those are correlated X's, and that's why we're seeing what we're seeing. Or it might be maybe a true or false, basically the same sort of exam, except for on paper. I will, however, provide for you on the exam every single data set that I use to generate the output. I'll give you all the output I think you should need for the exam. Yeah, you should be fine. And some students will not need to use the software whatsoever. But if you found as a tool, it's a good tool for you for the sake of answering the sort of questions the test has on it. Go ahead. Doesn't bother me at all. So you'll have the data sets and you could use them in any way you want. And there's some questions that will probably relate to data sets you actually know about. and you could look at. And if there's questions about hypothetical data sets, you can think it through, ask me to clarify during the course of the test. And if there are questions that are related to data sets that someone else created, did an analysis with, I might bring that to class. But if I don't have access to the actual raw data, I can't provide it to you. And so that's always, I guess, a possibility. But I'll certainly give you everything I have, which will allow you to answer the question sufficiently. So that's a good place to stop. And it is 1 o'clock. So enjoy the rest of your afternoon, and we will see you all on Tuesday.
I have one quick question.
Sure, sure.
Are we allowed to cheat sheet?